What I'm going to talk about today is specifically one piece of the weights and biases pipeline, the artifacts tool. So I'm going to show you how to use the weights and biases artifacts tool to track your ML experiment pipelines. Let's dive in. What are artifacts and why should you care about them? An artifact is a produced object, the output of a process. That's pretty vague. In machine learning, the most important artifacts are data sets and models. Usually, when people say artifact, they mean some big thing that's probably going to be represented by a binary file as opposed to text. We have Git and GitHub and other tools for versioning our code, and we can do a really good job tracking changes there. But when it comes to big binaries, Git is actually not a great solution. It's tuned to do well for code. What weights biases artifacts is basically like a Git and GitHub setup, but for artifacts rather than code. Rather than treating these artifacts as something that's separate from our development process, that's maybe almost unimportant or epiphenomenal on the side of that process that we version control and that we check in, these artifacts are like the Cross of Coronado from Indiana Jones. They belong in a museum. And that museum is the Weights and Biases platform, where we will store your artifacts for you and catalog them so that you, your team, and the ML community at large, if you so choose, can learn from all of those artifacts. After all, anybody who doesn't track training is doomed to repeat it, just like history. So the basic setup is that artifacts are either the outputs of runs or the inputs of runs. So a data set is a type of artifact that's often an input to a run, and a model is a type of artifact that's often an output to a run. But there can be all different kinds of artifacts, not just data sets and models. You could actually use artifacts to track your code if you so desired. But the key idea is that we have these two different types of objects. We have artifacts and we have runs, and the runs connect artifacts to one another. The basic setup is whenever you would do a weights and biases run, you can choose to log the inputs of that run. Basically, the default is you don't do anything, right? You don't track the inputs and outputs of your runs. You don't track the data set. You don't track the models. You could choose to include the data set as an artifact the run uses. And then if it produces something like a model, you can choose to include that artifact as something that the run logs. We're going to do a walkthrough of a complete end-to-end example of artifacts instrumented in an ML pipeline. And if you'd like, or actually, I encourage you to ask questions as we're going. Pipe up and ask, why did you do that? What other things could you do? Or to ask questions about particular use cases. If you're curious about it, I'm sure others are as well. All right, so let's start. Let's just run this quick installation here. Run anyway. The example I'm going to use is going to be based off of Francois Chollet's simple MNIST convnet example, but it could just as easily have been done in PyTorch. There's nothing framework specific about any aspect of our artifacts tool, and it could have actually been done in any other framework, not just Keras or PyTorch, or in pure Python. Some of the other folks in the company are fond of demonstrating this artifacts tool with all kinds of different things. Our CTO says everything is an artifact, if you really think about it. So there's nothing specific here to this simple Keras example, but I picked it because it's canonical. It's a baseline from which a lot of other examples might draw. We're going to start by logging our data set. We're going to have a training set, a validation set, and a test set. And we're going to log all of those. The MNIST data set, this is a well-known data set. It's stored on the internet. But then the specific breakdown of, okay, this is what I'm going to use to train. This is what I'm going to use to validate. This is what I'm going to use to test. That's something that's maybe a little bit more specific to a particular pipeline. For example, I'm choosing to have a training set of size 50,000 here. So what we want to do is we want to actually log this because we want to not only sort of say, all right, this is the training set I'm going to use, this is the validation set I'm going to use, this is the test set I'm going to use, but we also want to get it into our own file system and organization. And the artifacts system will actually organize all of the files for you. And so if you so choose, we can actually manage the location of all of the files to make it easier to track and use them across versions, just like Git can make it easier to track and manipulate files across versions. And so this first block of code here is just loading the data. I'm not going to spend any time really talking about this block of code because one, it's boilerplate kind of code in Keras. Two, it would be different if you were doing something different, if you're using PyTorch or something like that. I'm going to focus instead on the artifacts code. One thing I want to point out here is that the code for loading the data can be completely separated from the code for logging the data. So I've written a separate function here, load and log, that calls that function I defined above to load the data and just wraps it in the necessary material in order to log that data set in the artifacts system. What's needed in order to log data in the artifact system is basically 3 steps. Like any weights and biases run, we need to generate it with wanb.init. We need to initialize a run. Maybe if you've been using weights and biases just for things like sweeps or for logging your experiments, you think of weights and biases runs as being just for training, but actually a run can be any execution of any program. And so just downloading the data set, that's something that can be a run as well. And if you start instrumenting your pipelines with artifacts, you'll find that you actually have way more job types than just model training. So job type, actually, I dropped that there. That's a term of art in artifacts. Job type is an argument you can pass to wnb.init to say, okay, hey, this is what kind of job this is. And this is useful for organizing your artifacts pipeline. It's like a nice little label for those jobs that you're running. We also have a project just like any other weights and biases run. So that's not that different. The pieces that are different and new for artifacts instrumentation include creating our artifacts. So there's this new piece with the artifact system of the WNB API, WNB.artifact. And in this step, we're introducing, okay, this is the thing that we are going to log. We aren't pulling the data down yet. We aren't using it yet. We're just saying, hey, this is the artifact that we are going to be working with. I like to put this towards the beginning of the script. You could also put it at the end if you'd like, if you want to programmatically generate these things. Maybe it's easier to do it after. In this way of doing things, we're going to generate this artifact here. And then what we've got to do is we've got to add files to it. One mental model that I use for artifacts is that an artifact is like a directory. Rather than it being like a file, an artifact is more like a directory. When we want to add stuff to a directory, we need to call the new file method of that object. So when we want to add something to this artifact, we want to add it with new file. And the way that's done is very similar to the way files are added and written to in normal Python style using this with block here. So this gives us a file handle, and then we use that file handle with whatever we use to save that artifact. So these datasets are .npz files, so we save them with np.savez. We've got a couple questions in the chat. Could you give us an example where using a job type would be helpful? Is it like the stages of my pipeline? Does every stage get its own job type? I think that's a good way of thinking about it. It's like a stage of your pipeline. I wouldn't give a different job type to say if I loaded this data with a different data set size. So if I wanted the training set to be 40,000 instead of 50,000, I would give it a different job type. That would just give me different versions of the artifact, but it wouldn't give me a different job type. So I think pipeline step is the right level of abstraction to marry to these job types. Once we've stored a new file in the artifact, so we've said, okay, hey, artifact, here's one of your files, and here's the contents of that file. Then we want to save that artifact to weights and biases. So we want to say, hey, online on the weights and biases website, on weights and biases servers, I want to include this artifact among the things that I am tracking. And that's this log artifact command down here. Let me execute that cell, and that will both define that function and execute it. Just like any other weights and biases run, you'll see these URLs for the project and for the run. You'll see some information about the process's execution. And if we go to, say, that particular run, so normally if I were in weights and biases using a more typical training run, I would see a bunch of charts here. I would see the loss going down over time. Hopefully, I would see things like that. But this run doesn't generate any charts. What it instead generates are these artifacts like this one here. This data set has been generated here. The raw MNIST data set split into training, validation, and test. And so this information here comes from this WNB.artifact call here. I needed to give my artifact a name. What is this artifact called? And I needed to give it a type. And so these types help us split out the different kinds of artifacts that you're uploading The types that most people tend to upload are things like datasets and models, though you might have things like reports also uploaded. It's also useful to include a bunch of metadata here. Like here I wrote where this was obtained from. It was obtained by using the keras.datasets.mnist method for downloading the mnist dataset. And I also included the sizes as metadata. And that information will pop up here in the weights and biases web interface under the metadata. And that short description also shows up in this overview here. Right now, we've only really focused on what it looks like to log an artifact. Things get interesting once you start actually using them. So a couple of notes here on these different pieces. In this CoLab notebook, I've got it split up so that there's these little sections here. If you want to dive into greater detail about any of the pieces, you can dive in there. One rule of thumb for how to organize your runs and projects is to say that if runs are going to share artifacts, if later I'm going to train a data set on this model, then they should all fall in the same project. So I had to pick a project that this artifact corresponded to. All the rest of the artifacts I produce in this notebook are going to be in that project because they're all related to one another. This data set gets used by the model produces an output and a report, and all of that goes together. This keeps things simple, but it's not necessary. Artifacts are actually portable across projects. We also actually, I think, covered this second rule of thumb. The job type should be descriptive and correspond to essentially a single step of your pipeline. Here, actually, we're separating out the step where we load the data set, where we download it from the internet, from the step where we pre-process it. So I think you want to get a reasonable degree of granularity, but I think a high degree of granularity. Let's talk a little bit about some of the choices that we make when we create an artifact. When we create an artifact, we give it a name. That's what the first argument there set. The name should be descriptive, but you want to make it easy to remember and type. I like to use names that are hyphen separated so I can add a few details. And I also like to keep them as close as possible to variable names in the code. So we'll see maybe some examples of that a little bit later. This type here, it should be simple, more like dataset or model than say mnist data plus a timestamp. So when there's tiny changes like that, when it's say, oh, I'm going to download a slightly different version of the mnist dataset, I've trained a different version of this model, those are different versions of the same artifact. You wouldn't want to make them different types. I also mentioned that you could attach a description and metadata. The metadata is a dictionary. It just needs to be serializable to JSON. I try to make that metadata as descriptive as possible. And so we'll see some examples of how that works just coming up. And then lastly, we used artifact.newFile and run.log artifact to add the files to the artifact object and then to log it respectively. Because artifacts are structured like dictionaries, it makes a ton of sense to split the artifact up into many files. So I split into training, validation, and test because mnist is small enough that the entire training data set can fit reasonably in a single file and can even fit entirely in memory. But if I were working on something like ImageNet, I would have a much more granular directory structure. I would have maybe a different directory for each class. Those things would all be under a single artifact, the ImageNet dataset, but then it would have those subfolders in it. But when it comes time to scale, you really want to have your artifacts split up into lots of files. The new file thing, not that much else to say about it or about log artifact doesn't really have that many super important parameters to it. It's just a signal to us that it's time. This artifact is ready to go into the museum. It's been dug up. It has been packaged into a box and it is ready for exhibition. That's all for the log artifacts section. Now it's time to show you what it looks like to use a logged artifact. Artifacts in weights and biases, unlike artifacts in museums, are designed to be used, not just stored. So let's see what that looks like. What we're going to do is we're going to produce a pre-processed data set. So the raw mnist data set is actually not good for deep learning. The values go from 0 to 255 because they are integers. They are unsigned 8-bit integers. That's bad because most neural network weight initialization schemes and a whole bunch of other architectural choices kind of presume that your values are somewhere between -2 and 2 most of the time. So they assume they're normalized. There's also some stuff about the shape and the type of the labels that we want to adjust. And so rather than having this just be part of some script somewhere, I'm going to log this step, which is going to make it much easier for another member of my team or a future data scientist at my company or another researcher who wants to replicate what I have done. They can look and see, okay, this is how they pre-processed their data. Here's the script. Here are the inputs and outputs. Here's a bunch of metadata about it that's way easier to work with than just say, oh, here's a pile of scripts. I ran these to get my results. Good luck. We're going to log this pre-processing step. And once again, we're going to split out the step for pre-processing from the step where we log that pre-processing. That previous cell up there defined the pre-processing step. And then this one just wraps around that the necessary code to log it as an artifact. So once again, we've got wmb.init because we're doing this as a run. We've got a different job type now because we aren't loading data now, we're pre-processing data. And if I came along and I changed my pre-processing setup, then I would keep that as a pre-processed data job, but then I would just have a new version of my MNIST pre-processed data artifact. That artifact gets created down here at line 5. The processed data is another wmb.artifact as the same type. It's also a data set, but now it has a different name. It's the MNIST-preprocess artifact. It will have the same type that tells you that maybe two artifacts have some relationship to each other, and it helps us split out your different runs in our API. But it's primarily a cosmetic thing to separate out these types. The new stuff actually is what I really should be focusing on in this cell. So the new stuff is on lines 11 and 14. First, we have this new thing, run.use artifact. This says, hey, this is the artifact that I am going to use in this run. We're going to use the raw data artifact. So that's what I've named that variable here. I get this thing I can use to reference the artifact there when I call run.use artifact. And then the next step is to download the artifact, to say, okay, I want this artifact on my local file system ready to be used for a bunch of other stuff. So that's this raw data artifact.download. There's this .download method that makes sure that this file is present on the local file system. And then this last bit here just runs the pre-processing on every split. It pulls out the training data, the validation data, and the test data, and runs the pre-processing on it. That's what that looks like. One thing to note here is, what did I choose for the metadata here? For the metadata on this artifact, I chose the arguments to the pre-processing function, this steps thing here. You can see that gets splatted out as keyword arguments for the pre-process function. This is like a nice pattern, I think, to say, okay, some of the metadata that I'm going to associate with this artifact is the stuff that's necessary to recreate it from its inputs. Otherwise, maybe that metadata about just exactly which pre-processing you ran might get lost if you don't log it. It might be possible to recreate it from the information included in the rest of your logging, but I think it's always good to be as careful as possible here. I think of logging as a belt and suspenders kind of thing. You know, if you want to keep your pants up, a belt helps, some suspenders help, but what really helps is having a belt and some suspenders. You've got double protection. With artifacts, I like to log things as much as possible, especially small things like these keyword arguments here. Let's run this cell down here that passes those steps in and creates this artifact. You'll note there's this thing that says, oh, downloading large artifact, MNIST raw, 50 megabytes. And then that's done in 0.1 seconds. So what's going on here? That step there, it's called .download, but that's actually, you might worry that means that we're downloading a whole bunch of copies of your stuff. You don't need to worry. Before we actually download anything, we check to see if the right version is available locally. So we use hashing to make sure, okay, if I look for MNIST raw here in your artifacts folder locally, do I find something that hashes to the same thing as what's up on the servers? And if so, we don't download anything. As artifacts are created and logged, a little folder called artifacts in the working directory will start to fill with subdirectories, one for each artifact. Right now, my artifacts folder has this MNIST raw folder in it, and in it are the test, training, and validation data sets. The other piece was the run.use artifact. Both use artifact and download are a little bit simpler than the steps needed to log an artifact. Using an artifact is a little simpler. You just need to know which artifact you're going to use. And so the consumer of an artifact just needs to know its name plus the version of the artifact that you want. By default, the last version to be uploaded is tagged latest. You can pick older versions with a different alias like v0, v1 if you want to pick the first or the second version to be uploaded. These are kind of like Docker Hub tags if you've ever used Docker Hub. They're separated by a colon and they identify particular versions. So you might make a different version of your model that's ready for serving on TensorFlow on a mobile device with TensorFlow.js. You could tag it with that. You could tag it with the best version of your model. That might be another tag that you update. So as people are running training, if they find a model that works better than the one that worked previously, we tag it with best. Tags, you're free to use whatever you want. In the simplest cases, you can just stick with latest and always use whatever is the most recent version of the artifact. So the rule of thumb here is to keep aliases short and sweet and use custom aliases only when you want an artifact that satisfies some property. Otherwise, you can just go with a particular version number. So we've got a couple questions. How long will weights biases store my artifacts? So weights and biases, I think our intent here with artifacts is to be like the Louvre or the Metropolitan Museum of Art. We will store your artifacts indefinitely until the barbarians storm the gates and burn it down. So you don't need to worry about that. Another question, what if my data is sensitive and I can't send it over to WNB? How do I track my data pipeline in that case? That's a great question. Our primary version of our app, the one that all of our free users use, is this public online version. So what you see when you go to WNB.ai here, but you aren't locked in there. If you have your own cloud, we can deploy our weights and biases to your own personal cloud. And if you are air gapped or you have your own personal network that you do all of your data science on, we can also deploy weights and biases there. And both versions there have artifacts built in. Great questions. Thanks a lot. Now that we've logged and used an artifact, actually this artifacts tab on the run page is going to look a little bit more interesting. This new run here. Now, this run page has two entries on it. It says, okay, the input artifacts to this job included the raw version of the MNIST dataset, and the outputs of this job included the pre-processed version of the MNIST dataset. You can go and check out this version. It's got different information here on the overview. It's got different metadata. It's got now this table of metadata has the steps that were used to produce it. And then now one thing that's gotten a little bit more interesting is we've got this graph view of these artifacts. This graph view shows what were the runs in squares and what were the artifacts in circles that are part of this project. Right now, it's just at the level of types. So when I was saying that these types were primarily cosmetic, what I meant was that they get used in this graph view to separate things out. So if I'd given these things all the same type, there would only be one square and one circle. If I'd given, say, the pre-processed data set a different type than the raw data set, then I would see something that looked different. I would see two circles instead of one. So this is a sort of high-level view of what types of runs and types of artifacts are you generating, which is often like a useful overview of your pipeline. But if you want the actual details of every run that has been done on every artifact in this project that has been logged, then you can see that by clicking that explode button there. So right now you can see that I actually ran the pre-processing step before this demo, because you can see that the run that from the demo is down here, different sound 5, whereas there's this separate pre-processing step up here from when I ran this to check and make sure it was working. This exploded version of the graph lets you see your pipeline in precise detail. Let's keep going now. First, I showed you how to log an artifact. Then I showed you how to use an artifact. That's the full artifacts API, basically. What I want to show now is I want to show you how does this go all the way to the end of an ML pipeline. Before I do that, quick question. Okay, sick graph. Thank you. Can many people on my team contribute to the same set of experiments, i.e. can multiple people train different models that feed into the same pipeline? Great question. Yes. If you look at this little lock here, that says that this is a private project. For me, that means only I can contribute to it. If I were on a team of people, that would mean that other people who are on my team can contribute to it. And then you can also create a project that's public, and then anybody can contribute to it. Anybody who knows the name of your project and your name can find it online and can then use that and contribute to the project. So that's usually done for public benchmarks. We recently released a big public benchmark called Safe Life in partnership with the Partnership in AI. That group, they're doing this really cool benchmark around safety, around designing an RL agent whose behavior is safe and does not cause side effects. So that's an example of an open benchmark, and that would be something to which anybody can contribute. But you can set that flexibly who you want to contribute to your project. So let's continue on with logging now some models, so logging some training. This first cell here builds a deep neural network model in Keras, just a really simple ConvNet. Again, this comes basically from Francois Chalet's example. And we're actually going to start by just initializing the model, not training it. And that way we can repeat the training while keeping everything else constant, keeping those initializations constant. We're going to use WNB to track the run. And so using actually the WNB.config object to store all of the hyperparameters. And that config object is basically a dictionary already, right? If we just pass that to a dict, that becomes really awesome metadata. So when I use artifacts in my training pipelines or anything else that I would use that I was already using weights and biases in, I like to use that WNB.config as my metadata for my artifacts. This also shows another way to add a file to an artifact. You can save it on your local file system, then add that file directly with artifact.addFile. So just scrolling back up here, there's that line there, 14 has that. And the reason why I use that is there's this nice interface for saving models in Keras. And so the disadvantage of using add file is that if you use new file, the way that I did previously, then our artifacts setup will make sure that these artifacts are only kept around in one copy on your file system. If you start saving copies of it yourself, then you'll end up with one copy where you saved it and another one in your artifact file. In general, you want to use new file, but I wanted to include add file because it is an option. The way to get around what I just said about duplication is that once you've logged a file, then just delete it when you're done. And then you'll only have the copy in the artifacts folder. We built the model here. We logged the configuration of the model to weights and biases. If we go on the runs page and take a look at it, again, nothing has been logged yet. One nice thing that standard output gets included. So if somebody wants to look back and see some of the information that was logged to standard out while this artifact was being generated, we've got that for you. We automatically collect that along with some other files, including, because I use WNB.save, I also included this nice version of the model that can be put into the Netron viewer that we've incorporated into our tool. So you can view the actual computational graph of your neural network. That's a really nice tool. Instead of having to dive through some of these configuration files, you can take a look holistically at this graph. But then I think I wanted also to just point out, we've got this artifacts tab for this run that has the metadata. So now here is all of that config information. It's included, it's attached to the model. We've got this metadata here, and we've got that graph view. Notice that this is the same project, but it's a separate pipeline, right? The model and the data haven't talked to each other yet, so they're actually off here in this separate graph. If we want to get those things to connect, then we're going to want to train the model. We're going to use that initialized model, and then we're going to train it. We're going to do the same thing that we did before, where we both use an artifact and log a new artifact. But now it's going to be this training process instead of the pre-processing of the data. I think the thing that's interesting about this is that I'm going to use weights and biases tools to track this. So I'm going to use our WNB Keras callback here. I'm going to do things like track some of the inputs and what they were labeled, and track the loss and track system metrics. If you want details about this, check out our collab on integrating weights and biases with Keras or our YouTube video on the same topic. All right, so we're going to run two separate artifact producing runs. One actually that trains the model, and another one that consumes that trained model artifact by evaluating its performance on the test data set. I've been running these sort of one step at a time, every single artifact generation, every single step of the pipeline, one at a time. But actually, when you're running your pipeline, you're probably doing these many steps in a row. So I wanted to show you a little bit of what that looks like. The one thing that's interesting about this evaluation step is I'm going to pull out the examples that the network did the worst on in the test set, the hardest examples. So that's what this function does here. Pulls out the loss value, the actual examples themselves, and both what the network predicted and what the true labels were for those. So this is a really nice trick for actually diagnosing issues with your data set, where maybe there's some outliers or some weird parts of your data set, or for figuring out when your model is doing something wrong. So those don't have any artifacts logging features. The artifact logging features are in here. And now you can see I'm using all those pieces that we've used before. I'm going to use an artifact. I'm going to download it. And then I've got it ready to go. I do that again because I need to do that for the data. I need to do that for the model. And then I need to generate now a trained model artifact, that model trained with model.fit. And then as metadata, I'm going to use the config here. I'm going to include both the training config as one part of the WNB.config here. And then I'm also going to use the model's configuration. So I store that in the metadata of the artifact. I can access that here. And now that is accessible here. And what I'm just going to do with that is I'm going to pass it forward so that now the trained model also has all that information about its architecture included in its metadata. Like I said, belt and suspenders. So the rest of that, we're using .save and add file there. So same thing that we did previously. Then with evaluate and log, the main thing that we're doing, we aren't producing an artifact here anymore. We're just logging to weights and biases, this normal way one would without using artifacts. Okay, so let's run that code. It takes a little bit to run, it's a couple of epochs of training there. So I guess I'll just point out here this wnb.log call right here, lines 52 to 54 in this cell. This is where I'm logging those high loss examples. So what I'm doing is I'm going to wnb.image. So .image, this is one of the things we use to log media to WNB. You might already be familiar with wnb.log, using that to log, say, your loss or your accuracy on your test and validation and training set. You can also use it to log media. So this wnb.image here is logging media. It's saying, okay, take this hard example. This is I believe, NumPy array right here. And hey, interpret this as an image and give it this caption. The caption I'm giving it is what did the network predict, and then what was the actual correct label. So that's this wnb.image call here. You can see the details in the docs. Now we're done. That training has completed. We can see right here in the terminal, we can see that the loss went down, the accuracy went up. That's great. And the validation loss over epochs went down. That's good. Validation accuracy went up. We can also, of course, check that out on the actual weights and biases normal web app. So I pulled up the evaluation run here. What I've logged are those high loss examples. Before I do that, I want to instead first look at the run page here for the actual training runs. On the training run, I tracked that validation loss across epochs, and then I also tracked the accuracy. The other thing, weights and biases automatically picks up some of these system metrics, memory utilization, CPU utilization, disk IO, and GPU utilization, which are really great for improving the performance of your code if you can track this. We always capture that computational graph here. When you actually execute a model, we can notice that and grab that computational graph on top of having that Netron viewer if you want a prettier or more detailed view. And as previously, we captured that ephemeral standard outputs. But the new piece here for folks who are familiar with weights and biases is this artifacts page with inputs and outputs. Here's that trained model artifact. This is what it was all about. This whole setup, downloading the data, pre-processing it, all of that was there to make this trained model. Here's our final graph, nice looking graph. We've got all of our runs on the left side and the right side here. We had runs to initialize our model and to load our data. We had runs to train that model, to pre-process that data. The training script, we can see, takes in a model and returns a model. And a pre-processing data script takes in a data set and returns a data set. If you put good typing information into your artifacts and runs in that job type and type argument, then you get nice looking graphs here. If everything were just run and artifact, we would just have two things, a circle and a square with arrows between them. And it wouldn't be as easy to read what's going on. We can also explode that out and see them in precise detail. We can see in greater detail what specific runs actually. Daily Yogurt 6, it looks like, was the run that initialized it, whereas Fiery Morning 7 was the run that trained it. And then you can go back in the runs on your project and drill down what got logged on that run and what happened then. Of course, we also collect a whole bunch of other information. I'm on the projects level here, so there's not that much. But if I pick a particular run here, on that overview, there's going to be a lot more information here. So you can go back from that graph view, grab that run name, and then go and check out that run here and say, okay, oh, look, it ran on a K80. I actually didn't know. You get a different GPU every time you initialize Colab. So I actually didn't know what GPU I was on. Thanks, weights and biases. Version information about your OS, your Python, your WNB, and timing, duration, all this kind of stuff is here associated with these runs, and you can find them from that artifacts interface. So working off of that graph view here, let's take a look at it. This graph view here, we get this nice high-level overview that we can then use to drill down into the specifics of individual runs and individual examples, individual models, individual data sets. And this is a really useful tool when you've got a pipeline with lots of people interacting on it to generate data sets, generate models. This can be really useful for coordinating between people and tracking when changes got introduced and what those changes were. That's everything I had to talk about with the weights and biases artifacts interface. There's more stuff out there, so you can check out our docs for the artifacts API if you want to learn more. But this is a core set of artifacts features that you need to do pipeline versioning. And so our hope is that our tool, our artifacts tools, ends up in the position of something like GitHub and Git for regular software, that this version controlling of your data and of your models heals the same kinds of headaches that Git and GitHub heal. We hope you enjoy the product. Let us know what works and what doesn't, what you find useful and useless. And if at any time you're working on something with artifacts and you think, oh, a great feature would be, oh, if I click here, something happens. Or I don't know, there's a bug, there's an issue, there's something less than maximally joyful occurs in the process of you working with artifacts, click this intercom button down here and let us know about it. We reply pretty quickly, under 10 minutes is our current median reply time. And we really do take folks' input seriously. And it drives the changes to our products. People were telling us they needed something to do this kind of pipeline versioning, and that's why we built artifacts. Your intercom message could be our Jira issue and our new feature on our roadmap. Please put those in as you use the artifacts feature. All right, that's all I have for today. Happy learning and take care. Bye. Hey friends, Charles here. Thanks for watching my video. If you enjoyed it, give it a like. If you want more Weights and Biases tutorial and demo content, subscribe to our channel. And if you got any questions, comments, ideas for future videos, leave a comment below. We'd love to hear from you.